Everybody can see my screen, right?
Yes, we see your screen.
Awesome. So I've been working on artificial intelligence, machine learning, deep learning, and big data for about 14 years now. This was something that the CTO, when I was at KLA Tencor, asked if I could actually start a practice there. And emerging, it was even before cloud servers were available. Amazon was not there. Google was not there, nor Microsoft up in the cloud. So we essentially set up our own high-speed cluster in our data center. And so I want to talk about AI. I want to talk about machine learning and the work that I've done. I transitioned from the semiconductor industry over to smart kitchens, fully automated, fully roboticized kitchens. And I'll talk about that, the work we have done in that area as well. So I have a few slides, and so I'll try some of them. I'll speed up, and but I don't know. Questions are along the talk, during the talk, or after, Michael?
We're going to have a question and answer period after all the talks.
Nice. Okay. Perfect. So I'm going to talk about, just essentially show what the abstract that I've sent. I think most of you may have had a chance to look at that. I'll talk about big data. I'll talk about how semiconductors are made at a very high level and how it all ties together for artificial intelligence and machine learning for the semiconductor industry, and interestingly enough, for a host of industries. I'll talk about AI for the chip industry and AI for the kitchen. Chip is semiconductor chips fabrications. Talk about AI for the kitchen, and then I'll do business case, use cases, and trends, and wrap up. So this is the abstract. Michael asked me for an abstract, and I sent it. The gist of it is on the left side. It's really AI is really problem solving to improve business operations, efficiencies, and customer experiences using the exponential growth in data known as big data, and I'll talk about that, resulting in breakthrough approaches for artificial intelligence, machine learning, deep learning, which is starting to actually mimic how the human brain works. Not quite there. You may have heard of ChatGPT, how it essentially feels like you're talking to a real person, and the Turing test and all that. I won't touch on all those things, but I just wanted to kind of talk a little bit about that at this point, and the breakthrough approaches for AI, machine learning, and deep learning with applications of semiconductor chip fabrication and smart automated kitchens. So let's start. It's all about the data. So what do I mean by that? So this is an article that came in the Harvard Business Review, which said you can't manage what you don't measure. And so exploiting vast new flows of information can radically improve your company's performance. So the work that my team and I have been doing have been really focused on company performance, company improvement, so on and so forth. What do I mean about the data? So it's predicted, this is from IDC, the Data Center Journal, that by the year 2025, we will be at 163 zettabytes. Just a few years ago, we were 64 zettabytes. So what does this mean? Everybody here, I mean, people here may be aware of a zettabyte, but I wanted to kind of give an idea of what it feels like. So if a gigabyte, each of us, every one of us has computers. We have probably in a laptop, we probably have about 150 to 200 gigabytes of hard drive space. So if 1 gigabyte is the size of the Earth, then an exabyte is the size of the sun. And the amount of data by the year 2025, and this is just an approximation, 1,000 zettabytes equals 1,000 exabytes equals a zettabyte, and so the amount of data is expected to be about 163 zettabytes. Few of you may have seen the movie Oppenheimer, and I couldn't resist adding this. So Oppenheimer said this: if the radiance of 1,000 suns, and I said 163,000 suns, were to burst at once into the sky, that would be like the splendor of the mighty one. So to give you an example of what the data explosion is coming, is coming, and will essentially grow even significantly in the years to come. The promise of big data is really synthetic truths whose correctness cannot be determined without access to empirical evidence or external data. Simply to say, with the vast amounts of data that are available, we are able to get insights that were not previously available to us. And that's the promise, that's the excitement of data. And from that, leading on to machine learning, deep learning, and artificial intelligence. There are ways to define data. There's volume, there's velocity, there's variety, and there is veracity. And I'll talk about that in the next slide. So they're called the 4 V's of data. The volume, the data at rest, terabytes to exabytes of existing data to process. As an example, at KLA, we would essentially get petabytes of data every minute. So we would fill up servers and we would throw that data away until we essentially put a team together to try and understand what insights the data was giving us. Velocity, data in motion, streaming data, milliseconds to seconds to respond. Data in many forms, structured, unstructured, text, multimedia. You can actually draw insights from all of these. And data in doubt, veracity. A lot of data sometimes could get corrupted. And how do you account for that? How do you correct for that? All of these things come into play. The term that is used in the artificial intelligence community is ELT, which is extract, load, transform. But before you do all of that, you have to cleanse the data. You have to really look at it. Is the data making sense? I want to go into the art of making semiconductors. So we've talked about the data. Semiconductors, as everybody's aware, is the brains of everything today, are starting to become the brains of everything today. Chips produced on a single wafer. A single wafer is cut from the wafers, from this wafers, and a single chip is cut from the wafers, covered in a package to become a semiconductor product. The process from going from the left side to the right side is extensive, and it is a whole slew. And I won't go through this except to say you form films, you expose organic chemicals that are laid on it called photoresist to get patterns. You etch into the substrate, you implant ions to actually create source and drain. Then you build up layer upon layer. And this can go for some of the most complicated chips. This can be repeated over 150 to 200 times. So the challenges of chip manufacturing. So why is AI and machine learning so critical, so important now? The right side on the top shows all of the steps that go to, in a graphical format, all the steps that a semiconductor chip goes through to actually become, to essentially be fabricated. The challenges today are scaling, interconnect, and overlay. And what I mean by that is the chip sizes are getting smaller and smaller. They're getting more dense. And the ability to connect from one transistor to the next, and then overlay these layers one upon the other is become the critical problem of today. Right now, TSMC is Taiwan Semiconductor Manufacturing. They have facilities in Taiwan, but they're now starting to have facilities in Arizona and Texas from the CHIPS Act. They just announced the 3 nanometer. We're now talking a 3 nanometer transistor size, or essentially a node size, as they call it, is the size of a strand of DNA. So it's that small. So what this has resulted in is extreme challenges in semiconductor development. On the left side, you see metal gates, they're all starting to have transistors work at those extremely small levels, the 5 nanometers, the 3 nanometers, and so on and so forth. And you have an enormous amount of challenges. And what the industry has realized, what we realized when I was at KLA, was that the amount of data that we get on the bottom right graph is a wealth of information that is collected from the system, from the wafer, from the environment, that you can then process to understand how the semiconductor yield, which is the most important thing. We want all of these chips on a wafer to yield at the end of the process, how the yield is being affected at each step of the process. So the challenge was the amount is the shrinkage in the semiconductor sizes, in the transistor sizes. How do we meet these challenges? The approach that we took was, what is the data telling us? And using that information, look for ways to meet the challenges in chip manufacturing. So I want to step aside before I get into the heart of how we did this. Define what artificial intelligence is. It's very clear to everybody that if a machine can perform cognitively as a human being performs, we would associate that with intelligence. And because it's a machine, it's an artificial intelligence. So things like perceiving, reasoning, learning, interacting, problem solving, creativity. And then technologies that AI has enabled, robotics, are working towards enabling autonomous vehicles, computer vision, language, that's ChatGPT right there, virtual agents, machine learning. What has enabled the AI revolution is the ability to have enormous amounts of data that are accessible because of accelerated computing that is available to us. And what the industry has done is actually write algorithms that parse the data, learn from it, create rules, and then artificial neural networks, which tends to mimic the human brain. It trains, it learns through training, extracts, analyzes, and predicts. So prediction is the key, and it's really probabilistic and stochastic in nature. So statistical approaches to actually predict what the data is telling us. So we have descriptive analytics. We do that on a day-to-day basis. We have Excel. We can actually see what is happening between two variables, multiple variables, etc. Where AI machine learning start to come into play is predictive, looking at classifications, looking at regression to actually say what inherently or anticipate what will happen, and then prescriptive, tell the organization, this is what the data is telling us. This is what the organization or the people under or the business needs to do to improve its yield, to improve its operations, so on and so forth. The three types of machine learning, which is really a way to do the prediction, do the prescriptive analytics, is supervised learning, where you take a small set of data, you train the algorithm on the data, and then you feed it new data. So it tells you what the output, it predicts what the output is going to be. Unsupervised learning, wherein you do not do this training, you write the algorithm, you give it the data, and you see what the algorithm is telling you. An example of supervised is like a logistic regression. Even linear regression would be supervised. Unsupervised is like k-means or KNN, k-nearest neighbors. And then there is reinforcement learning, wherein you actually provide rewards to the algorithm so that you essentially have it converge to the result that it is. I mean, essentially get to a predictive result. Yeah. The real promise of AI and machine learning is to leverage mathematical algorithms to translate a set of input variables never seen before into concrete predictions. How did we do that? So first and foremost, we actually built this. This was before Amazon or Google Cloud were there, with over 136 CPUs in a server, over petabytes of memory and petabytes of disk space, and then wrote the algorithms to actually do the calculation. So this is a very high-level slide of fast data analytics. It talks to extract, load, and transform. So it takes the data, it selects from the data, and then it tells you where the data that of interest is located. And finally, it essentially takes it, writes algorithms, SQL, advanced analytics, and it provides you the output. And the output can be in a variety of forms. So this is a variety of data that actually tells you how input variables and output variables are graphed together. So you visualize, you comprehend, and you predict. So for the AI for the chip industry, here are two examples that we did. One was the problem of overlay, wherein as you lay one layer down to the next layer, we want to make sure that the wafer, because it goes through a lot of thermal processes in plasmas, laying down films, it doesn't distort. So the previous, on the leftmost side, the linear regression, the linear approach that was being used, essentially you can tell from the actual that it is not really predicting what the actual is going to be. So we use the classification method called random forest that took the data and predicted what the actual wafer geometry is going to be at each step. So this was a practical approach that we took from the machine, from the system, from the wafer, each step to tell how the wafer was performing as it went through each process. And as I told you before, there could be about 200 steps. Each step repeated approximately up to 200 times, causing the wafer to distort. Okay, then finding defects. That was the other approach that we did. As a defect could be a deposition where it shouldn't be, or a hole in the chip where that shouldn't be. So the way we would do it is acquire optical image sets, compare with design files, create the library, extract defect features, and then acquire the defect images and compare to the actual. And these defect images are taken with very advanced light microscopes, bright field and dark field, different ways to actually get contrast on the wafer, and also electron beam electron beam microscopy. I shifted over from semiconductors into smart kitchens. So I want to take a few minutes to talk about that, the work we've done. So today in kitchens, as the slide shows, most processes are manually monitored, crowded, dirty, user interface is difficult to use. And what we have pioneered is the ability to do predictive maintenance and to make sure that the kitchen is never down. So the stove burner will fail within the next week. We have sensors. So essentially, we put together a fully automated kitchen. This was before the pandemic. We had to actually shut it down after the pandemic. But we had every single function and robots doing all of the cooking. We had sensors. The sensors would send data to the cloud. We would do the analysis in the cloud. And then we would send back, this is what is happening. This is what you need to change. We would provide ingredients for the chef to create the meal. And we would essentially preheat all of the ovens, all of the different kitchen equipment to get it ready for the order as it came through, and forecast orders and inventory as available. So I want to wrap up with the business use case and trends. So some of the algorithms that, and I've touched on a few of these, like linear regression is used to understand product sales drivers. Logistic regression, the finance industry is using for likelihood of loan repayment, decision trees on how to hire, who's the right candidate, simple neural networks on predicting healthcare enrollment, for example. Naive Bayes is to classify and filter spam emails. And essentially, this is a sampling. There are enormous number of algorithmic approaches that can be used for doing machine learning and deep learning. So where are the trends? The trends are hyper automation, using AI to speed up and simplify tasks, cybersecurity, and then the latest trend is called Industry 4.0, which is the intersection of AI, machine learning with Internet of Things. Really a way to say, can you put sensors in every intelligent sensors that monitor temperature, pressure, humidity, air purity, sound changes, vision recognition, to state a few. So I think that's what I wanted to talk about. It was quick. Each of these I could spend a lot of time on, but I'm hoping this gave everybody a flavor of some of the things that are happening in the industry. So I want to end with one slide. This actually came out of a Duke University course in the spring of 2019. So we've seen this, the technological capability. Dilbert cartoon, Dilbert says, schedule a meeting, never mind, my phone took care of it. To autonomous driving, autonomous vehicles, and then this is the worry, when our AI systems or computers controlling becomes sentient. Just the humorous slide that the professor was showing at the class, in the class. So.
Okay, thank you, Krishna.